Okay, in the last video, we talked about the idea of laser cooling, that we can use the fact that light carries momentum to exert forces on atoms and exploit the Doppler effect to use those forces to only slow atoms down. By this method, we can take atoms from speeds, around the speed of sound in sort of room temperature air and get them down to velocities of centimeters per second. That's millionths of a degree above absolute zero. So this laser cooling technique is extremely powerful for slowing the motion of atoms, which is the thing that we need to do if we want to do tunneling experiments and see these atoms penetrating a barrier that they classically should not be able to get over. Now, if we want to do this, we need lots and lots of these very cold atoms, but there's a problem with just doing this Doppler cooling and optical molasses technique, which is that the molasses will cool the atoms, but it doesn't confine them. Right, and the reason for this is the same thing that limits the temperature, is that they get these random kicks from photon emission. So every time the atom absorbs a photon and slows down as it's getting cooled, it gets kicked in another direction, right? And that process is going to lead the atoms to sort of wander around kind of randomly, right? And an atom that starts out moving left to right is going to absorb and slow down, but then it's going to get a kick in some random direction when it re-emits and say, it picks up some upward component of velocity. Do this again, well, it slows down again, but maybe it picks up a component of velocity going to the right. And this happens again and again and again and again, and these atoms will sort of wander around randomly each time they move a little bit in between absorptions of photons, and that random walk will eventually lead them out. This is a phenomena that in math picks up the name drunkard's walk, right? And it's a diffusion process, sort of like a person who's had too much to drink, who's just sort of aimlessly bumbling around. Eventually, they're going to find their way out of a crowd of people or to wherever it is that they're going, just while randomly bumbling about it. If we want to collect a large number of atoms, we need something to stop this drunkard's walk behavior from taking them out of the range where they're being cooled. We need to add an extra force that will confine the atoms to allow us to collect really large numbers of them. So how can we do this? Well, there's a couple of ways, and this video is going to be about different ways of manipulating atoms and exerting forces on them that can help confine them in space. One thing we can do is we can use what's known as the Zeeman effect. All right, it's spelled Z-E-E-M-A-N. Looks like it might be Z-Man, but he was Dutch, so it's Zeeman. All right. The Zeeman effect is something that happens because atoms behave like tiny little magnets. All right, which means that the exact energy of the state of an electron in an atom depends on the strength of the magnetic field in which it finds itself, and the alignment of the orbit and the electron with that magnetic field. That means that if I can make a magnetic field that varies in space, right, I can make the energy of those atomic states depend on their position. Right? If I do that, I can create what's called a magnetic trap. Right? I have a magnetic field that's low in the center and gets higher as you move out toward the edges. If I put atoms in that, right, the ground state energy will be low in the center and get higher as you move out toward the edges. And that means that an atom that starts in the center and starts to move out, well, its internal energy will be increasing due to the interaction with the magnetic field. Right? That increase in internal energy has to be balanced by a decrease in the external energy, which means it slows down. But that means it feels a force that depends on where it is in this magnetic field, pushing it back toward the center, right? So these atoms will, in this magnetic trap, will behave sort of like they're rolling around in a bowl, like they're marbles rolling around in a bowl. They want to be at the point of lowest energy, which is right in the center where the magnetic field is a minimum. Right? You can use this magnetic trapping to hold a sample of cold atoms, provided you get them cold enough to begin with. The one issue with this is that the forces that you can exert with magnetic traps are not very big, right? So this is something that you have to start with atoms that are already cold, right? So if you could get a bunch of cold atoms, then you can turn on a magnetic field that has a minimum in the center of the trapping region, and then you'll trap those atoms. But the atoms have to be very, very cold to begin with. You can't do this with atoms that start out hot. Because the forces that you can get from a reasonable size magnetic field just aren't that big. This is, however, absolutely critical for Bose-Einstein condensate, which is a phenomenon that we will talk about in a future piece of this module. And the crucial technology for that is, in fact, these magnetic traps. But we need something that'll get us a bigger confining force than magnetic traps. And one way to do that is to take this magnetic Zeeman effect and combine it with the forces from light, which can be very, very big. Right? We talked in the last video, the force from light acting on a rubidium atom can produce an acceleration of tens of thousands of times the acceleration of gravity. Right? Really, really big forces. So if we can combine that with this magnetic behavior, we can make something that will confine the atoms more effectively. We're able to do this, it turns out, because the picture I've been using for atoms is a little too simplified. Right? Atoms don't have just single energy levels. Each of these energy levels has multiple sublevels, right? If you took chemistry in high school or whatever, you spent a lot of time in intro chemistry drawing these electron configurations. You're putting an up arrow and a down arrow in these little electron shells, and S shells can hold 2 atoms, P shells can hold 6 electrons, right? And then on and on and on. This is looking at these sublevels that go with the different states in atoms. And this has to do with the angular momentum of the atoms in the orbits. The critical thing about this is these sublevels have different Zeeman shifts. So if I take a 2-level atom and I put it in a spatially varying magnetic field, I get these 2 levels will split into multiple sublevels. Some of them go up in energy with increasing magnetic field. Some of them go down in energy. So I can take the simplest cases where the ground state has only a single level and the excited state has 3 sublevels. And when you do that, you get 3 different Zeeman shifts that depend on the strength of the magnetic field. So if the magnetic field is big and pointing in that direction, then the red state goes up and the blue state goes down. If the field is big and pointing in the opposite direction, right, then the blue state goes up and the red state goes down. So I put on a spatially varying magnetic field, I get these states that split apart, and some of them go up in energy and some of them go down in energy. Then I can use the polarization of light to pick which sublevel I excite the atoms to. So I take my pair of counterpropagating laser beams, but I make one of them polarized one way and the other polarized the opposite way. And when I do that, then the red laser that's coming in from the left here will excite atoms only to the red sublevel that's going down in energy as you move out to the left. The blue laser coming in from the right, on the other hand, will excite atoms only to the blue sublevel, which is coming down in energy as you move to the right. Then I detune my laser to the red of the rest frequency of the atoms. And you'll see there's a point where the detuning of the laser and the down Zeeman shift of the particular sublevel, those things cross, right? That dotted line indicating the laser detuning crosses with a particular sublevel. At that position in space, no matter what speed the atom's moving, it is guaranteed to interact with that laser, right? So an atom that starts to move out to left, even if it's going very, very slowly, right, when it gets to that point, is going to absorb light from the red laser coming in from the left. When it does, it feels a force that pushes it back toward the center. On the other hand, if the atom's trying to go out to the right very slowly, at some point it comes into resonance with that laser and feels a force that pushes it back. Now I have a force that depends on position, right? I move away from the central region of the trap. If I try to get too far out, there's a force that pushes me back in. These light forces can be very, very big, right? The magnetic field isn't doing anything here that's pushing on the atoms itself. The force is all coming from the light, right? And it's coming from the light. It's just the magnetic field is giving you a little bit of spatial dependence that makes the force depend on the position, so that it always pushes the atoms back toward the center. Right. This magneto-optical trap is what I showed at the beginning of this. This is a famous photo of atoms in a magneto-optical trap. And you could trap millions, hundreds of millions, billions of atoms in one of these traps, and they're held in there by light forces. And this has become a real workhorse for atomic and molecular physics these days, right? People who study the properties of atoms and molecules, their field has been absolutely revolutionized by the ability to collect samples of, millions or even billions of atoms at extremely low temperatures in these magneto-optical traps. So it's completely transformed the field in the last 30 years. There's one more kind of force we can look at pushing atoms around with, and that's very important for the tunneling experiments we're gonna talk about, and that has to do with the nature of light as an oscillating electromagnetic field. Right? So we know that light is an oscillating electric field and also magnetic field, and we know that magnetic fields shift the energy levels of atoms. It's called the Zeeman effect. So we can also ask, does the interaction with light shift the energy levels, right? Does that electromagnetic character of light allow it to change the energy levels of the electrons? The math that goes into this is a little complicated, but the answer is very straightforward and useful, and it's yes, it does. And more than that, the shift that you get depends on the frequency. So if I have a two-level atom that wants to absorb light at a particular frequency, and I shine in light that's red detuned, a little too low in frequency, that has the effect of pushing those states apart, right? The energy difference between those states gets bigger by a tiny amount, but by a measurable amount if you're dealing with lasers. On the other hand, if I have that same atom that wants to absorb a particular frequency and I put in light that's blue detuned, that's a little too high in frequency, that will tend to push those states together, right? So red detuning pushes states apart, blue detuning pushes them together, right? And this again is something I can use to exert forces on atoms, right? In the same way that I use spatially varying magnetic fields, right? So if I take a beam of light, like a laser, and focus it down, right? If I look at a cross section of that beam, say where that yellow dashed line is in the picture up here, what I see is an intensity that varies with position, right? So it's brightest right in the center of the beam, and it drops off to zero as you move out to the sides of the beam. Well, that light intensity will also shift the energy levels of the atoms. And if I detune that laser to the red of the frequency that the atoms want to absorb, it will tend to push those states apart. The ground state will go down in energy, the excited state will go up in energy. On the other hand, if I tune the frequency a little too high, so it's blue detuned, then the ground state will go up in energy and the excited state will go down in energy. This means I have an internal energy for these atoms that's changing with position. And just like with the magnetic trap, right, this gives me a force, right? If an atom is in the center of the trap where the ground state energy is very low, as it moves out, right, the internal energy comes up, right? That has to be compensated by the external energy, the kinetic energy of the atom decreasing. That amounts to a force that's slowing the atoms down, pushing it back toward the center of the trap. So if I take a focused laser beam, right, and detune it to the red, I can make an optical trap where the atoms have their lowest energy right in the center where the light is the brightest, and they'll tend to be confined there. On the other hand, if I take a blue detuned laser, the energy is highest in the focus. That's an optical barrier that tends to push atoms away from the spot where the light is the brightest. So these give me forces that I can use to push the atoms around. Now you could ask, well, if I'm shining a laser beam in here, isn't that also pushing the atoms along the direction of the beam? And in principle it is, but there's a nice feature of these shifts, which is the light shift that changes the energy levels, scales like the intensity of the light divided by the detuning. So if I make the detuning twice as big, the energy shift that I get is half as big. Right. On the other hand, the scattering force, right, the probability that the atom absorbs a photon and gets a kick in the direction of the laser, that goes like the intensity over the detuning squared, right? So if I double the detuning, I tune the laser twice as far away, the amount of scattering force I get goes down by a factor of 4, right? So I get half the light shift, but 1/4 the scattering force. So what I can do is I can take these, I can tune the laser miles away from the resonance and crank the intensity up really, really high and get a substantial light shift right, and get a force from that that can be big without having to worry about any scattering force, right? The atoms won't absorb any of the photons. They won't get pushed in the direction of the beam. So I can make optical traps and optical barriers by using very bright lasers that are detuned from the resonance by a very large distance. What do I mean by large distance? In some cases, it could be hundreds of nanometers away, right? Or tens of nanometers away, just depends on how bright your laser is, right? If I want to make the light shift big at large detuning, I also need a large intensity. So a friend of mine uses an industrial cutting laser that's like 100-watt laser, super dangerous death ray that focuses down to make optical traps for rubidium atoms. So, and that's just because the wavelength of that cutting laser is way away from anything else, and can be pretty much wherever you want as long as you have enough laser power to get the light shift that you want. So those are the tools that we use to push atoms around. We can use magnetic fields to make magnetic traps that will confine atoms, and that'll be critically important for talking about Bose-Einstein condensation, which will be the next thing up. We can use a magneto-optical trap, which uses magnetic fields to add a little position dependence to these very strong light forces. And that allows us to collect huge numbers of atoms in these magneto-optical traps. And then we can use just purely optical traps where we use far detuned lasers that are very intense to make either an optical trap that will hold atoms in a region where the light is very bright, or an optical barrier which will push atoms away from the spot where the light is bright. And you might notice that both of those things would seem to be extremely useful when we start talking about these tunneling experiments. So those are the tools that we use to make cold atoms, the Doppler cooling process and laser cooling, and then these magnetic, magneto-optical, and optical traps that we can use to confine atoms and push them around. And those are the key pieces that we need. Now you'll notice that we still are talking about laser-cooled atoms that are only millionths of a degree above absolute zero, where really we need to be able to get atoms down to billionths of a degree above absolute zero. Getting there involves a completely different kind of cooling process and a phenomenon known as Bose-Einstein condensation, and that is the subject of the next class. So come back for that.